Okay, hi friends. Today we are going to discuss about the application of Gauss theorem, in which now we are speaking about the electric field intensity due to an infinite line charge. That is, we have to obtain an expression for electric field intensity due to an infinite line charge. For finding out the expression for electric field intensity due to infinite line charge, let's have a line charge like this, and it is positively charged. And in order to find out electric field intensity by using Gauss's theorem, we are considering a closed surface, that is, a Gaussian surface is taken in the form of a cylinder around this line charge. Assume that this is a cylinder in which the line charge is placed like this, and this is our cylinder. These are the two flat surface of the cylinder. Cylinder is having one curved surface also. Then we are trying to mark the direction of area vector on the two flat surface and on the curved surface. Area vector, it is a vector which is drawn perpendicular to the area. If the area is like this, area vector will be perpendicular to it. If area is like this, area vector will be perpendicular to it. Therefore, at the upper flat surface, the area vector will be perpendicular to that area. That is, the area vector's direction, it will be like this. And on the upper flat surface over here also, the area vector, it will be denoted like this. And at the lower flat surface, we could represent the direction of area vector like this, and over here also the area vector denoted like this. Then on the curved surface, the direction of area vector, it will be like this. On this curved surface, we could denote the direction of area vector like this. Now we have marked our area vector at all positions on the cylindrical Gaussian surface. Next, we are marking the direction of electric field intensity at all the points where we have marked the area vector. What is electric field intensity? It is the electrostatic force of attraction or repulsion felt by a unit positive charge placed at a point. Therefore, the direction of electric field intensity at this particular point, we have to assume a unit positive charge over here. And if we are placing a unit positive charge over here, this positive charged conductor will repel it. Therefore, the direction of electric field intensity at this particular point, it will be like this. And if I am placing a unit positive charge over here, this positive charge conductor will repel it. Therefore, at this point, the direction of electric field intensity is like this. And over here also, if you are placing a unit positive charge, this positive charge conductor will repel. Therefore, this is the direction of electric field intensity. Similarly, if you are placing a unit positive charge over here, this conductor will repel. Therefore, this is the direction of electric field intensity over here. And over here, we will have electric field intensity like this. And over here also, if you are placing a unit positive charge, it will get repelled, and this is the direction of electric field intensity. Thus, we have marked the direction of electric field intensity and area vector on the two flat surface and on the curved surface. Then let's write the mathematical form of Gauss's theorem or Gauss law. Gauss law is saying the total electric flux enclosed by the closed surface is 1 by epsilon 0 times charge enclosed, or we could write phi is equal to integral of E dot ds, that is equal to q enclosed by epsilon 0. Phi is equal to integral of E dot ds. We have studied it from basic theory of electric flux. E is electric field intensity, ds is area vector, q encloses total charge enclosed by this closed surface and all. Then from this we are taking integral of E dot ds is equal to q enclosed by epsilon 0, and in this case we are having a cylinder, therefore the total integral of E dot ds we could write it as integral flat E dot ds, that is we are having two flat surface, therefore 2 into integral flat E dot ds plus integral curved E dot ds. Since there is only one curved surface and two flat surface, that's the reason why we are writing 2 flat integral of E dot ds plus curved integral of E dot ds, that is equal to q enclosed by epsilon 0. Then let's analyze what's happening in flat surface. In flat surface, you could clearly see E and ds, are they perpendicular or parallel? They are perpendicular. In this flat surface also, or in the lower flat surface also, E and ds are perpendicular. In flat surface, E perpendicular to ds, therefore the angle between E and ds, it should be 90 degree. Then what I could write is integral flat E dot ds, it could be rewritten as integral flat E ds cos 90, and you know the value of cos 90, cos 0 is 1 and cos 90 is 0. Therefore on the flat surface, integral of E dot ds, it will become 0. Since cos 90 is 0, E dot ds, the whole integral of E dot ds will become 0. Therefore in flat surface, this is the situation. Then in the similar manner, let's look what is happening in curved surface. In curved surface, in the curved surface, E and ds, in the curved surface you could clearly see E and ds, are they parallel or perpendicular? They are parallel. Therefore E is parallel to ds, that means the angle is 0 degree. If the angle is 0 degree, integral curved E dot ds, it will become integral curved E ds cos 0. The value of cos 0 is 1, therefore E ds into 1, that is integral curved E ds. That means in short, integral curved E dot ds is integral curved E ds. Integral flat E dot ds is 0. Substituting these values over here, we'll get, since flat is 0, we don't have to write this, and we'll have to write integral curved E ds, that is equal to q enclosed by epsilon 0. I could write like this. Then from this expression, I could take that E outside. I could write E into integral curved ds, that is equal to q enclosed by epsilon 0. The reason for I am writing it like this is E, since the conductor is passing through the center of the cylinder, this distance and this distance will be same. Therefore the magnitude of electric field intensity over here, it should be equal to the magnitude of electric field intensity over here. In short, electric field intensity is constant. If there is a constant inside the integration, we could take it out. That's the reason why I am taking this E out. E into integral curved ds is equal to q enclosed by epsilon 0. Then what is integral curved ds? That is the curved surface area of this particular cylinder. For saying about the curved surface area of this cylinder, let's consider the length of this cylinder as L. L is the length of the cylinder, and the radius of this cylinder, we are taking it as R. r is the radius of the cylinder and L is the length of the cylinder. Then how can you find out the curved surface area of a cylinder? It is circumference into length. Therefore, the total curved surface area, that is integral curved ds, means the total curved surface area of the cylinder, that will be 2 pi r into L. Therefore, instead of curved surface integral of ds, we could write 2 pi r into L. That means I could rewrite this expression as E into 2 pi r L, that is equal to Q enclosed by epsilon 0, from which I could write E is equal to Q enclosed divided by 2 pi RL epsilon 0. Q enclosed divided by 2 pi RL epsilon 0. Then pay your attention over here. Assume that this is a line charge. This is a line charge which is having a length L, and the total charge of this line charge is Q. L is length of line charge, Q is the total charge on this line charge. Then we could define a term lambda. Lambda is linear charge density. Linear charge density can be obtained by total charge divided by total length, or linear charge density is the charge per unit length. What is linear charge density? It is the charge per unit length. The charge in a unit length, it is called as linear charge density. Lambda in this situation we are denoting for linear charge density. Why I am saying it is because you could see the Q enclosed over here and L over here. What is Q enclosed? It is the total charge enclosed by this cylinder. What is L? Length of the cylinder. Therefore, in this case, Q enclosed by L, Q enclosed divided by L will give you the linear charge density of this charge rod. What is Q enclosed by L? I could represent it as, or I could replace it as linear charge density. That means I could write E is equal to, instead of Q enclosed by L, lambda by, let me write it like this, 2 pi epsilon 0 r. This is our expression for electric field intensity due to an infinite line charge. But you may wonder, you have drawn a finite line charge, then why you are saying it, this is the electric field intensity for an infinite line charge? It's because in this formula, is there a term which is length? No. That means this formula is applicable for finite line charge and infinite line charge. Since we are representing in terms of linear charge density, this formula, it could be used for finite line charge or infinite line charge. That's the reason why we are using it as electric field intensity for infinite line charge. What is E? E is electric field intensity. What is lambda? Lambda is the linear charge density, charge per unit length. What is R? R is the perpendicular distance where we have to find out the electric field intensity from the line charge. The perpendicular distance from the line charge where we could find out the electric field intensity. And from this expression, it is clear that electric field intensity is depending on the distance from the line charge. And if I am writing it like this, the electric field intensity is inversely proportional to distance. And if we are plotting a graph with electric field intensity, and distance, we could obtain the graph like this, that is, it is inversely proportional. We have studied inversely proportional graph. This is R and this is E, means inversely proportional graph. It will be like this. Okay. Therefore, electric field intensity due to an infinite line charge, it will be lambda by 2 pi epsilon 0 r. Hope you have understood this.